We've just defined what it means to take irrational powers of real numbers, right? So that means that all of our exponential functions are defined for all real numbers, no matter what my base b is here. B to the power x is some number I can just conceptually think about and even calculate in some instances. So let's take a derivative. I don't have derivative rules for these functions yet. So I'm going to have to go back to my limit-based definition. So let's look at the limit as h goes to 0. I have f of the quantity x plus h minus f of x, all divided by h. So let's fill in the formula for my exponential function. And I'm going to leave the base as some constant b. So this is equal to the limit as h goes to 0 of b to the power x plus h minus b to the power x, all of this divided by h. So I'm going to use my, excuse me a bit here. I noticed I was missing something in the window. Here we are, sorry. I'm going to use my rules for exponential functions, where b to the power x plus h is the same as b to the power x times b to the power h. But that means I can factor out a b to the power x out of all of this. And that means that f prime of x is equal to b to the power x times some limit. There's no more x's in here. That is really weird. And think about this. The derivative of an exponential function is itself times something. Times what? I don't know what. We'll find out. So this right here, this limit, is going to be a constant. It'll be a different constant depending on what b is, sure. But there's no x's in this limit. It's the same constant no matter where I'm trying to calculate that derivative, no matter what the value of x is. So for right now, I don't have rules for this kind of a limit. Yes, the numerator is going to 0. The denominator is also going to 0, but I don't have much algebra here that will be able to help me out. I would have to resort to computer calculation. So, suppose someone did sit down to try to calculate this limit. Let's try it for both the numbers, the bases b equals 2 and b equals 3. Here in this table, whoever this person is has calculated out values for the variable h. H is going to 0, so 0.1, 0.01, 0.001, and so on. And here are the corresponding values of that difference quotient. 2 to the power h minus 1 on h, and respectively 3 to the power h minus 1 all on h. Well, the limit in column 2 appears to be, well, at least some number that starts out 0.69. Again, I am zoomed out far enough that maybe only the first 2 digits matter. Nice. For b equals 3, it looks like I'm getting to a limit where maybe the first couple of digits are 1.10. So these limits are converging, at least numerically. We're just testing this out with a computer. Okay. Well, I notice that for b equals 2, this derivative, right, this value of the derivative at x equals 0 is 0.69 and change, which is a number smaller than 1. For b equals 3, my limit gives me about 1.10, which is a number bigger than 1. So this ties back into my observation from before that these exponential functions have different slopes. So if I choose the base, if I'm allowed to choose the number b, I theoretically would be able to control the value of this limit. Well, wouldn't it be very nice, fascinating in fact, to have a function which was its own derivative? Well, exponential functions could probably do that. Derivative of the function being its own self. But that would require me to have this limit, this b to the power h divided by 1, all divided by h, that would need to equal 1. Does that make sense, right? Derivative of an exponential function is, well, derivative of b to the x is b to the x times this kind of a limit. I would want this kind of a limit to equal 1. So, well, I should think that numbers that are, so 2 is definitely too small, right? I get 0.69 as my limit. 3 is definitely too big. I get 1.10 as my limit. Why, maybe something in between would work better. And here is what I was saying before, that d dx on 2 to the x is about 0.692 to the x. Here again, our squiggly equal signs are saying that I'm zoomed out too far to really tell the difference between these things. And here, d on dx of 3 to the x is about 1.103 to the x. My squiggly equal sign tells me that I'm too far zoomed out to really tell the difference between those things. I would like to pick a b such that that limit that I get is 1. And one of the ways we can get the number e is that e is the number that does what I want. The limit, as h approaches 0, of e to the power h minus 1, all divided by h, this will equal 1. Now, your textbook works through this slightly differently, with e being the solution of a different limit problem, and then shows that that solution is also the solution to this problem. What we need to keep in mind is just that e, the constant e, is the special number where y equals e to the x has a slope equal to 1 at x equals 0. So this, amongst all of the exponential functions, there's a different exponential function for every positive number. And amongst all of them, the function e to the x is special because it is its own derivative rather than being a multiple of its derivative. So every exponential function, its derivative is some number times the original function, and that's really cool in its own right too. We'll be talking about exactly how to find that number in a bit. But e to the x is the very special number where the derivative of e to the x is itself. Oh,